You have my presentation?
Yes, we have.
Now it's even better?
Yep.
All right. So I'm going to talk about motorized resistance and assistance and how we can apply that to deceleration ability. I work as an associate professor in Norwegian School of Sports Sciences, but I'm also involved in this company called 1080 Motion. So I'm going to talk a little bit about some of the research that we're doing in this domain as it pertains to portions of change of direction, and then also show you how this kind of technology can be applied. And it's actually going to feed some of the questions that was raised to Jonas, and I thought he did a great job of answering those. So this is one way where you can actually apply horizontal overload or assistance. So I'm gonna talk a little bit about that. Now I can't see everyone because I'm in this presentation mode. So if you have any questions, just not scream, but say hello, and then we'll answer. Current tests, we know this. Long in duration, many turns. We get an overall measurement that doesn't really tell us too much about the quality of deceleration, and thereby maybe not provide us with sufficient actionable insight. So this was kind of our starting point of applying motorized resistance, because we then took, and Jonas was mentioning this, the 505, where we have this initial acceleration to a decel, which then subsequently is followed by reacceleration. Now, the good thing here is that you have a turn that you can isolate in quotation marks, one leg that is going to be very important in doing this, or even though it's multiple steps leading in. So it gives some information about a left and a right turn. And like Jonas was pointing to, there are certainly technical aspects of this. The current measures do not really have any phase information, so we don't know how the athlete was behaving in that quote-unquote deceleration phase as compared to the reacceleration phase. And currently they use the 180 turn. And also, if I want to overload this, there is currently hasn't been any ways of doing that. So that's where I apply my academic and also my involvement in this company. And this is the 1080 Sprint. What is it? It's a black box that you can wheel out on the turf for the hardwood or wherever you are. It's an electrical engine that is attached to a drum. On that drum is a line. That line is then attached to an athlete, and then he or she can do whatever they want because the line is 90 meters. So we have a lot of freedom here to move. What it does give us, since it is an electrical engine, I can set loading parameters differently from the assisted versus the resisted, which means that I can pull you harder towards the machine and give you a lighter when you go away from the machine, which is something that I'm gonna come back to. So being able to set loading parameters differently in the different phases, here is the reference concentric and eccentric. You can use resisted and assisted to pertain to deceleration and acceleration behavior. So that's the load component. The next one would be the type of resistance that you apply, because we can program the engine to do normal resistance, meaning that it behaves like a mass in a gravitational field. And we could also program it to be isotonic in nature. The isotonic is good that it, you'll have resistance when the acceleration drops. However, that inertia when you're trying to turn is going to be less, which is why we actually created a new type of resistance mode that mixes normal with isotonic. So you have inertia in the turn, but once your acceleration drops in that reacceleration phase, you still have the resistance because it switches to isotonic. Another thing that you can also play with is speed, meaning that you can set a maximum speed, and I'm going to get back to that, how that can be applied. So what we did is that we took the 505, and I do cross my fingers, and I hope that this will work for you and that you can see it. This is 3D kinematics in a lab. Here, the person is coming running. Imagine this little box pulling you in over here. These are 2 AMTI force plates. And here we go. Because we want to document what's going on. So we're doing this to validate the whole procedure. Because the intel that we get from the sprint in doing this looks like this. So this is a 505. This is my son. This is age 12. So Jonas, I can understand why you use your family as guinea pigs. I can relate to that experience. There will be videos of him later, actually. So here are 2 trials. Don't pay too much attention to the values here, but the point is that here I can look at the speed development, and the colored one, green and blue, is the deceleration component. Here the velocity changes direction. Let's call this the reacceleration component. So now I can look at the time in a certain phase. I can look at the average of velocity for that whole phase, or I can look at smaller intervals. And in this particular, this is 2 trials. He was not very familiar with it, but you see there is a certain trait of fingerprint in these curves. And I think in these continuous curves, there's going to be a lot of good information hidden. So then to our little experiment, and this is very preliminary data, and we're working on them right now. And due to the COVID-19 situation, it's been a little bit of wrench in our data collection. But anyway, if we look here, this is one subject, and we did this being pulled in with 3, 6, and 9 kilograms, so absolute numbers. We didn't normalize the load in this experiment. And this line then indicates, okay, this is where the person had this change of direction. And then on either end, on either side, within this interval, in the deceleration component and the reacceleration, I think there's going to be information hidden that can tell us a story about deceleration capacity and the change of direction capacity. And here's another subject under the same conditions that behaves just a little differently. Obviously, when you do this towing, the electrical engine, we get speed measurements, but we also get information about force and power and acceleration. So I totally agree with Jonas when he's speaking of that power component coming in. So the purpose of this was maybe to look at this component. So I want to look at that Decel component, how you do and how you move in. And then we've created this model because we have multiple projects coming up. This is rather crude, but the point is that you have a deceleration component and then the reacceleration. Here we have to really think about, and we have to keep our sport, analyze that. What kind of directionality is it? Is it an anterior, posterior, and lateral? What kind of movement behavior is it? And then how do I look when I turn? I know there are steps leading into it, like Jonas pointed to, but this leads to some sort of transition, which then has the effect I might move and continue movement in the same direction, or I might change my directionality, and I also might change my movement behavior. So how we've been working on this deceleration is we've used this robotic technology to provide horizontal overload. And then we've started with stability, where we look at bilateral landings to unilateral, like Jonas was talking to. And then also the directionality will, based on the base of support, if I go forward, my base of support is going to be greater as compared to going sideways. And then as we move up, or we make it more difficult, we can obviously increase load, and then that will decrease the rate. We can set the rate a little lower. And that's actually another component of using this technology, is that I can pull you in at a certain rate. I can pull you in at 5 meters per second. I can pull you in at 6 meters per second. And then communicating, I think that's a very important point that was brought up, the communication with the athlete. If you go faster, you're going to get a little slack. So they get a sense of how fast that they can go. So you can then gradually progress them, go faster and faster and faster, which then gets me into the power component. Then some progressions, I agree with Jonas. The rate of the decel, here you can certainly use distance, which will in due time then, or will impact time. You can use external loading to resist and assist. So if you resist the movement, you will obviously make the decel easier, and if you assist it, you're going to make it more difficult. So the stability first. Everyone can still see my video, John? You can see my screen?
Yes, all good, still all
Oh, great. So from a stability perspective, we know that hop and jump tests are used for dynamic postural control assessment, but it's also power assessments. So here you have my son, and he's been jumping away from it. So that obviously have an acceleration focus, so that can make it easier. So this is more towards maybe the rehab component, early portions, and then you can do locomotive patterns. You can be walking, running, lunging, side shuffling, and then come to a stop, balance. Then you progress to that without an external load, and then you assist, meaning that the person is going to turn around and is going to move towards the machine. So jumps and hops, since there are considered also power measurements and power tests, I will then present them later when I talk about strength, speed, and power. And in this context, endurance speaks to number of reps. So let's see if these videos will work. So this is assisted. Just again, very, very basic. Just focus on landing. And Jonas certainly comment on the technical execution here, and I have some comments as well. And then so you can go from bilateral to a unilateral behavior. There is certainly something to be desired in terms of the technical execution here, but the point is how you can use that to get horizontal overloading. Let's see if I can move forward. Hold on a second. There you go. And then locomotive patterns. Here we can use, and I love the video analysis, Jonas. I think that's brilliant. And here you have different cone distances. And the cool thing here is that with the assistance, you can actually use speed and how speed changes, because as it is a robotic system, the precision measurement is very accurate, which means that I can know which position they should start to slow down, and then I can actually give them feedback, because that information comes up right away. I know if they actually turn on the brakes when they were supposed to. So here is just some constraints to have them work a little bit harder or a little bit or not so hard. I realize now that this is probably just a side shuffle, the same kind of perspective. Now, towing, that works on deceleration, because if I'm being pulled in from over here, I don't have to accelerate myself. That allows me to not waste any energy on the acceleration, but then focus on the deceleration. So this is how we use it, and this is a very different example, non-team sports, but in speed skating, we've been using it to tow them on the home stretch or the long stretch, because they don't want to waste any energy on the initial acceleration, because they want to work on the turn. So they're being pulled in, let go of the machine, and then they work on the turn. So this towing allows you to be more focused on the deceleration component, because you don't have to work on accelerating yourself as much. Then this next one I really like is the eccentric overload. So within a specific movement, so here you have a locomotive pattern, you have a 505, for instance. You can then set the eccentric or the pulling force towards the engine or the machine a little bit more. And then they have to and then the load, as they turn, as they reverse the movement, the load drops, and it's going to be lower for them to actually do that reacceleration, which allows me to target and be more focused on that deceleration component. And again, this is my son. It's a opportunity sample. in this COVID-19 situation. So I wanted to keep it short and sweet. So this was basically deceleration. So directionality, the movement behavior, what transition do you have, and then what do you end up doing? So you can work on one or the other, or you can work on both. And then we all know that putting some sort of decision making into the mix while being under these conditions will allow me to get some good intel about agility. So that was my short and sweet presentation. Well, that was 15 minutes. So if you're interested, you can get some more information on these home pages. So I'm just gonna end the show. And then I'm gonna see, where did you go? There you go. Did I stop my screen share?
Yes, you did. So
Perfect.
Thanks very much for that, Ola. Any questions from you folks? Anything that's hopping out that you'd like to ask on now? Okay, I'm happy to lead in with a couple of questions, Ola, if that's okay.
Absolutely.
Okay, so you mentioned about this signature. I'm sorry, you used the word fingerprint. So yes. Individuals have a distinct, I presume it's individual specific fingerprint to their high intensity decelerations. What is the key differentiating factor between people who are great decelerators versus people who are average decelerators? If you were to pick a couple of metrics that differentiated, what would they be?
That's a great question, and we are trying to explore this now by testing different populations. So we're looking at this first step is to look at velocity and then look at accelerations, and then look at probably then combining velocity with mass to look at change of momentum. And I've been discussing this with Damien. To be honest with you, and I think it's important to be honest, I don't know what's going to be the best one to differentiate, but that's why we're starting this validation process. So we can take this machine and we can apply it to different populations. And from that, I think as a group, we can figure that out.
Okay.
So, and I think it's also situational dependent. So if you saw the curve of one of those individuals, it was a very abrupt deceleration, and that might be good in certain situations, but it might not be so good in other situations. And what's the long-term consequence of it? I don't know.
Well, I would imagine that what you want is to create an athlete with the capacity to apply the brakes as they see fit in a given situation. So they may need a high ceiling level of deceleration capacity. So again, in your research and the data you've gathered, are you seeing, is it feasible for athletes to change deceleration capacity through training? And if yes, and I'm hoping and presuming the answer is yes, people can change it, any perception on what are the key types of training modality that are most effective in enhancing deceleration ability?
I think it's going to be that combination of technical execution that Jonas was talking about, because we've seen that actually impact change of direction historically. And we're designing a intervention study now to take place in the fall, where we then try to actually break out and tease out the importance of applying that horizontal loading. Because I think that's going to be specific to the situation. We haven't applied it on a big scale, but we've seen that people spend shorter time in the deceleration, and they're better in the acceleration component. And one of the reasons why we actually test with different loads is for us to actually tease out what is it that we're going to be targeting. Are we going to be looking more into the force domain? Or are we going to be looking more into the power domain? So that's the reason why we actually use different loads there, because I want to look at the force velocity relationship of that reacceleration. And I'm going to use that as an outcome. I don't know if that answered your question, John.
Yeah, no, it does, and I guess it's not fair to expect specific answers.
Yeah.
So no, it does answer my question.
Because it's a very new area for myself to actually explore, because we've been a lot into this linear work, looking at sprinting, looking at the acceleration component. But this deceleration to the reacceleration has been largely underexplored using a horizontal loading that we can dial in very nicely. And knowing what's going to happen on the other end of that kind of intervention, here I'm just basing it, or the intervention is going to be based on specificity principle and directionality of force. Obviously, there's going to be a vertical component to it, but at the end of the day, I have to slow myself down horizontally. So that's going to be kind of where we probably set up two interventions, looking vertical as to horizontal, and see what falls out on the other side. That's the plan, at least.
Okay, well, again, apologies to everyone for being greedy here, but I've two other small questions. One is around asymmetries. I'm not sure if you can pick up asymmetries well with the 1080 kit, but if you can, just your perception of what's happening there. Is there a legacy left in from injury, be it minor or major injury? And is there any particular remedial types of training that you've seen being effective? So again, that might be a tough question. So first of all, is there an influence of asymmetries, either preferred leg or prior injured leg? Yeah, and then the second question, which is, you mentioned in one of the drills that you can pull someone in an acceleration and then take the load off when they're you can pull someone into the deceleration and then take the load off when they're re-accelerating after the turn.
Yeah.
So it seems to me that is potentially a means of reducing neural fatigue, if you want to use some term like that, but where you can get quality training in, but you can perhaps more specifically target the training and reduce the overall neural load and fatigue load on the athlete. Would I be correct in jumping to that conclusion?
I think you will be correct to jump to that, because if you want to target deceleration, that's a wonderful way of doing it. Because then you get the execution of actually making that turn, and then you can have a lower load to actually accelerate outward. Back to your asymmetry. Absolutely, we see asymmetry coming in. So the short answer to that question is yes. What I usually then, if you say you do a change of direction test, whether that is a 180-degree turn or a 135 or a 90, because we played with all sorts of different turns using the same system, I complement that with unilateral hop tests under loaded condition, 3, 6, 9 kilograms or 4, 8, 12 kilograms. And then what we're seeing is a pattern of the direction that I made the turn and also the effect on hop tests. So we're seeing they seem to coincide, if that made sense. So then you can go from an isolated test to, you can do just a landing test, and then you can look at the behavior of how I was able to absorb that speed and come to standstill. Then you can look at the acceleration component and jump away from the machine, and then look at my quote-unquote concentric capacity. So we've been working on that systematically, and then piece that puzzle together and look at that overall behavior of the system. So yes, you do see asymmetries, certainly. And I've tested it on myself. I play football at a very, very low level, so very subject to injuries. So when I myself, I actually tested it to see if we can pick up on some of my dysfunction, and certainly yes. And I've done that with my patients and athletes here in Oslo as well.
Very good. I think we have a question there from Nick. Do you want to jump in, Nick?
Yeah, thanks, John, Ola. Just something come to mind really, like we have speed reserve and how we can calculate speed reserve. I'm almost thinking here that like Jonas's drill of, in, accelerate, stop, back pedal, in, accelerate, turn away. A lot of my drills I've done in rugby and soccer and stuff is then have an opponent running at them or the ball's coming to them. Be interested to look at the different strategies. Because I don't think anyone's mentioned this yet, of doing just a straightforward ability drill and then match that with that person's strategy if you have a player running straight at them so they don't know when they've got to stop, or a ball is just being passed into their feet so they have to decelerate to control the ball or turn, or they catch a ball in their hand. I just wonder if there's some kind of deficit there or concept there that might be worth looking at between those two sort of different scenarios.
No, and I think that's where I ended up with my last slide, and this is where we have. I work at the Norwegian School of Sports Sciences, and upstairs, literally, it's the psychology or sports psychology department, and we're looking at integrating some of this decision making and putting this system in with that. As soon as we've validated it, then put the system in and then integrate decision making into it. And so I think that is certainly the next step here. But at the end of the day, I think training in a movement pattern similar to what you need, and then provide an overload to provide a buffer, and then at the same time coach them on technical execution. Because if you coach them on technical execution, that's going to show up on the numbers right away. That's the beautiful part, and that's back to this previous conversation about buy-in from the athlete. If they see that, what the coach told me really had an impact on my numbers, you're going to get a buy-in. So that's how we've been using it a lot too, using the numbers to get buy-in, so the athletes really understand and says like, oh, that might be relevant. I don't know if that answered your question there, but that's the next layer that we're going to target.
Jonas, I think you have a question. You'll have to unmute again. Yep.
Yeah. Just two things. One, the eccentric overload where it pulls you in and then it lets go. We've got 1080. It's actually right next to me, and that for me is a great tool, because I don't know if it's officially packed, but there's definitely this feeling that the high recruitment you have to find to decelerate yourself, and then now you've recruited and you've created large effort, then suddenly there's no load, you really get this explosion out of the hole. And so I think as a strategy for almost pre-activation, if you want to get in and out of a hole, don't wait until you're in the hole and sink into it, let it pull you in and then try and get out of it. Instead, be active, be aware, be ready for the next step. I feel like that tool, that's the only reason I started doing the banded overloads, is because I was shown that function on the 1080 a few years ago, and it was like, okay, yeah, this makes so much sense. It makes so much sense. So just wanted to add my 2 cents again.
No, I agree with you on that one, Jonas. It's largely underexplored territory. So if you're thinking like research project into this domain and how you can progressively load this, the stage is yours. Really, there are so many opportunities here.